Hey, boys and girls, and today we are going to learn about pedigrees. Pedigrees are basically family trees that are charts that are used to trace and track genetic traits over time. And so you probably have seen sometime in the past maybe a family tree, but this one has a family tree that's shaded in with names and sometimes they're colored in, and those colors indicate that that person has the trait of interest. Now, typically, we look at things that are diseases, um, whether we look at something like hemophilia or some type of cancer, or even just color blindness, etc. Whatever it is, these are traits that we can trace from as far back as you want, all the way to today's current generation. Now, you'll notice on the chart there are various symbols. This presentation itself, if you can take your screen and make it half screen so that you can watch what I'm doing as you fill out your chart. That's probably the easiest way to do. Simply drag the top of it, put it to the side. That way you can follow along. I'm going to put mine in full screen just so that I can show it as big as possible for you. So feel free to pause the video, play it faster if you'd like. Rewind it to see if there's anything you missed as you go back and fill this out. We will do this together, so it's going to be interactive. There are parts you're going to have to fill out, so do follow along as we go through this. So like I said earlier, a pedigree is a chart that uses symbols to represent people to show the inheritance of a single trait over time, over many generations. Pedigree charts, they're commonly created to show patterns of specific genetic disorders and traits. They can be used to predict probability. Now, once we kind of figure out what their traits are, what they have, we typically then refer to a Punnett square to make a better prediction of what the outcomes can be. So that's why we studied Punnett squares first. It's really important you have a strong foundation on Punnett squares because doing a pedigree without a Punnett square can be challenging. Most of it's done mentally, but there's many different possibilities out there. So make sure that you feel comfortable with knowing how to complete a Punnett square in order to do a pedigree. And so some basic symbols in a pedigree chart: circles represent females, squares represent males. When you look at this chart here, go ahead and click in this box. How many males do you see in this pedigree? Go ahead and pause the video and fill out your answer in that box there. Alrighty, so hopefully you got the answer correct. Let's take a look here. You should notice that there are roughly 3 males in that chart. So, on a pedigree itself, you'll see some lines that go across. A horizontal line is a line that's typically what we call a marriage line, but obviously today not every couple gets married, and so we call that a marriage line or a line of reproduction. Those two, a male and female, got together and had a family. The vertical line connects parents to children. So just be aware that those lines that go across represent reproductive lines, and lines that go straight down connects parents to their children. When we look at twins, we have to talk about fraternal twins. Those are non-identical fraternal versus maternal, which is identical twins. And we look at twins, you don't see this so common, but you do see them in pedigrees. A identical twin set will have a line connecting both of them at the bottom, and non-identical twins have that triangle line that comes straight down and connects both of them, showing that their DNA, once again, for identical twins is 100% the same. So just keep that in mind. That's why we look at the DNA for those twins. So go ahead and take this arrow and drag it down onto this pedigree, which shows us the marriage line. Go ahead and do that in your slideshow. Now, in a pedigree chart, if I'm going too fast for you, by the way, make sure you pause the video, go back and do that last step. If you didn't do that, feel free to speed it up if this is going too slow for you. In a pedigree chart, children are listed from left to right, from oldest to youngest. So the child that was born first will be on the far left, as you can see here, indicated by this arrow. Also, if you'll notice here, we list them by generation. Generation 1, Generation 2, and Generation 3. We use Roman numerals to represent which generation you all have here. So here you have the parents and children, and then from them, you have the grandchildren here and generation number 3. So, who is the oldest child? Go ahead and take a moment, look at this chart, type in their name down below in this box. As I said earlier, Roman numerals represent generations. So take a look at this pedigree. How many generations are shown in this chart? Go ahead and type your number down here below. So, as I said earlier, a pedigree chart can be labeled as shown below. This helps identify each individual. Sometimes we have names, sometimes we just have numbers. A lot of times this is done in privacy. So, unless it's a close family, like your family tree, then you'll have names there, or unless it's a case study. But many times we recognize each individual as being Roman numeral I1 or 1 you can say, Roman numeral 1 2, etc., to represent who is who on this chart. So, is Roman numeral 2 4 a male or a female? We're looking at this individual. Are they a male or female? Type in your response down here below. If you need time, pause it. If you're good with the pace, just go to type it in and follow along. So, some pedigree charts may not be labeled, and this is quite frequently, but you can still identify individuals. So, this person over here, notice where their position is. They're in generation number 2. They're the first person on the left, so they have Roman numeral 2 1. So, fill in the blank. Is Roman numeral 3 1 a male or a female? Now, as I said earlier, the whole purpose of a pedigree is to track a trait that's being passed down over time. And so there's kind of a couple ways we'll do this. If a person has the traits, females, they'll be shaded in all the way. Males, likewise, if they have the trait, they'll be shaded in. Sometimes we know that somebody's a carrier for a trait, and they'll be halfway shaded in. If we get a chance, we'll talk about that in a little bit. People that do not have a trait shaded in typically means they do not have the trait. But I must also say, sometimes we do not know if they have the trait or not. They can be carriers. And if they are a carrier, we would shade it in half of the way. A lot of times with pedigrees, we just don't know. We don't see the phenotype. We don't see the trait displayed on them. So therefore, they're not affected. Therefore, we don't shade them in. So, as I said earlier, if we do know, in fact, somebody's a carrier for the trait, which means they have it in their DNA, but they're not showing the trait, it's not in their phenotype, we can then shade them in halfway as a person who is a carrier for that trait. In this example, the trait that we're looking at here is freckles. So, how many children in the second generation have freckles? Go ahead and type in your response down below. In this example, you can see those people that have freckles. If you said 2, you were correct because there's 2 children that had freckles. Notice this male over here married someone else that's not a child from the offspring of mom and dad. So only 2 children had freckles. They have freckles, but they are not a part of this family. Being married to this male makes them a part of this family, but they are not the direct offspring from this father and this mother over here. So a trait in a pedigree can be either recessive or dominant. Remember, that the traits that are shaded are the ones that are being, the traits that are traced are the ones that are being shaded. And so traits can be now what we call autosomal, which means they run on the 44 pairs of chromosomes that we have. That 46 pair of chromosomes, those chromosomes are the sex chromosomes, the X or the Y. So as you know, we have 23 pairs of chromosomes, and 22 of them code for your body, your skin, your eyes, your hair color, all that stuff that makes you. In that 23rd pair of chromosomes, at 45 and 46, that I said earlier was a pair, that 45 and 46, those code for X or Y. X or X, male or female. That's what they code for. Those ones can be sex linked. Now, remember, when we look at dominant traits typically cover up or mask recessive traits. One classic but bad example are like brown eyes to blue eyes. And so, if brown was dominant to blue, here we have somebody who's heterozygous, capital B, lowercase b, brown eyes would take over blue eyes, which is typically a polygenic trait, but we'll get to that later. And so, as we look at different types of inheritance, one goal is to look at a pedigree and understand how is that trait inherited over time. Is it dominant, autosomal dominant, which means it's not on the sex chromosomes? Is it autosomal recessive? Once again, not on the sex chromosomes. It's on the main 22 pairs of chromosomes. Or is it sex linked? And we're going to look at some patterns here to help you identify what is what. So, an autosomal dominant pattern, you must have at least one dominant allele. So, anyone up here can be capital AA or capital A lowercase a. Having one of those dominant alleles means they have the trait. Now, I'm just simply using the letter A as an example. It has nothing at all to do with this pedigree. It's just simply giving you something to start with. And so these individuals up here can have that dominant or that heterozygous trait. So when we look at an example of a dominant pedigree, what we typically see is that it's usually in every generation. What we don't see are parents who don't have the trait and then kids pop up with the trait. That is the biggest indicator of a dominant trait being passed down. We can have parents that this one's recessive and this one has it. They have a child who does not have that. We can also have parents who both have it. Let's say they only had one boy, for example, this child over here. It's very possible parents can have it and the kids not have it. In that example, both parents would be heterozygous, capital A, lowercase a, and that child over here could receive that lowercase a genotype. So that's just one example of how we can tell what's dominant. In something that's recessive, as I said earlier, somebody who's recessive will typically see a trait pop up kind of out of nowhere. An example. What I mean by that is if you look at individuals 8 and individuals 9, here's a clue. Mom and dad do not have the trait, but all of a sudden it pops up in one of their children. In generation 317, this female has the trait when both parents did not have it. That is the classic clue that it is a recessive trait. Autosomal because it runs not on the sex chromosomes, but on the 22 pairs of regular chromosomes in their body. Finally, sex linked is one of the most precarious ones to find out, but you typically see a pattern. Remember, to be sex linked, we typically see most of those diseases run on the X chromosome. It simply has way more space. The Y chromosome is truncated, it's small. There's not a lot of space to fit genetic material. And so most of the X linked or sex linked traits run on the X chromosome. So for a male to get it, he only has one X chromosome. Therefore, if he gets that trait of interest, he will have it. Females, on the other hand, it's quite rare. They have two X chromosomes. And so for a female to actually have any of those X-linked disorders that we learned about earlier, one being colorblindness, they have to have both X-linked X alleles to actually have that, which is not that common. And so when you look at a chart that targets only males, it typically skips generation, and you see a male have it, it skips this person over here, another male has that. Remember, the male got his X chromosome from mom, not from dad. And so you typically see it go from grandmother to son, and then the dad gives it to his daughter, the X chromosome, and she's typically a carrier. Now, not shaded in these examples, which is perfectly fine, because in this example here, we're more focusing on those that do have the trait versus those that don't have the trait. And so, remember, heterozygous means you have two different alleles, a capital letter and a lowercase letter. Homozygous means you have the same two capital letters or two lowercase letters. And so, some helpful hints, as I said earlier, if an individual is homozygous recessive, then each of the parents must have at least one recessive allele. If an individual shows the dominant phenotype of a trait, then at least one of the parents must have that dominant phenotype. If both parents are recessive, then all of the offspring will also be recessive. So, take a look at this chart here. And in this pedigree chart, the trait that we're looking at is albinism. Albinism, as you know, is a pigment that typically is when somebody lacks the certain pigment to give melanin, and so therefore, basically, their skin comes out pale. So, in albinism, is albinism likely a dominant or recessive trait? Take a look at the pedigree chart of inheritance. And then once you see that, analyze that, feel free to pause the video. How would you classify this as dominant or recessive? Okay, if you said recessive, you were correct. If they have the dominant A allele, that's normal pigmentation. If they have the recessive A allele, that would code for somebody that has albinism. Now, take a look at this chart here, the same chart we just saw. What is the genotype of person 1, 1? Roman numeral 1, 1. What would be their genotype now that you know? If you missed what we just shared, go back to the previous slide and take a look at what I shared about the traits, the letters, or the alleles. If you said lowercase a, then you were correct. Since it's a recessive trait, the genotype must be homozygous recessive. So in this pedigree chart, as I said earlier, the trait that we're tracing here as albinism, if a Roman numeral I or 1, 1 is lowercase aa, then each child will have at least one of that lowercase a's given off to them, as you can see here. We don't know. We do know that this person has at least one dominant allele. We don't know if they have both of them. So, what is then the genotype of the person here in I2, this individual over here? As I alluded to, you probably got it. They can be homozygous dominant or heterozygous. We know they're definitely not homozygous recessive because they do not have albinism, but they can be either or given the fact that their children do not carry the traits. Now, this is the most difficult thing with a pedigree, is a lot of times we don't know the traits of offspring or somebody else unless it's one of interest, unless they show the phenotype. Also, we won't know the traits unless they have children. A lot of times for recessive traits that pop up, we don't know if somebody carries it, and that's why pedigrees can be challenging to find out exactly what somebody's genotypes are. So, go ahead and take a moment here, take a chance, and fill in the genotype for persons, individuals 2, 1, and individuals Roman numeral 2, 2. What are their What's their genotypes? Go ahead and type it in down in the box below. If you typed in capital A, lowercase a, then you're correct. That would give us the best indication because we know they received one recessive trait from mom. Given the fact they do not have albinism, we are certain they have one dominant allele. So, just a couple fun facts and wrapping this up here. Autosomal recessive traits usually show up in later generations, and they can come from parents that do not show the traits. Sex-linked traits are usually recessive, as I shared earlier, but some are dominant, and the ones that we cover in class will not be the dominant ones, typically, that we'll look at. Sex-linked traits usually show up in males rather than females, as I shared earlier as well. Take a moment, go ahead and drag and drop the genotypes to their appropriate location based on the information given here. So take a look and drag them to what you see here. What could indicate the genotypes of the people above? Pause the video if you need to do so. So now we have dimples as an autosomal dominant trait. This pedigree chart traces the trait of having dimples. In the text box below, explain why the genotypes in generation 1 are false. Why can that not work out? Take a moment and type in this box. Give me a sentence, a good rational answer, why we know that these genotypes in generation 1 are not true. Once you've completed that, you are done with your note-taking portion of this. Take a moment to review your answers, make sure everything's done. Head on over to the other activity. You'll complete that, and you'll turn that in. You'll be wrapped up for today. Questions? Let me know.